Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for coming, and it is my great pleasure to introduce Professor Joseph Laviola from University of Central Florida. So Professor Laviola is an SAIC faculty fellow in the EECS department there at the university. He is visiting us on a short trip to collaborate on a project, an interdisciplinary project on building drawing intelligence that combines sketch recognition with some learning theory. So Professor Laviola is a leading expert on sketch recognition and its applications to building intelligent tutoring systems. And today he's going to tell us a bit more about his work.
Okay. Thank you, Sumit. So, welcome. Thank you for coming. What I want to talk today is on moving towards using mathematical sketching, which, if you don't know what that is, I'll define it in intelligent tutoring systems. And I actually gave a talk here at Microsoft maybe about 5 years ago on mathematical sketching and something called MathPad. And at that time, we were interested in trying to develop dynamic illustrations for a variety of physics concepts. And now what I want to talk about is sort of, I'm going to give you a little bit of history to see where we were, and then we're going to look and see where we are right now and where we want to go in the future. And we've sort of developed a new system. We call it Physics Book. My student Salman is the chief person on the project. It's his PhD work. So pen-based interfaces is sort of the area that one of the areas I work in, and we're talking about interaction with a stylus or perhaps your finger using a tablet PC or interactive whiteboard, or various touch tablets. And one of the interesting things that I've seen over the last couple of years is that pen-based computing, pen-based interfaces, or pen-based interface research is sort of maybe not as important anymore, or people aren't doing it as much. And people are all focusing on multi-touch and touch-based interaction. But I still believe that there's a significant amount of work to be done in the pen-based computing world, specifically when we're talking about applications that actually take advantage of that technology. And one of the things that it takes advantage of is it allows you to mimic pencil and paper with one of these tablet computers or interactive whiteboards. And they're really good at entering 2D notations, so things like mathematics, chemical diagrams, drawings, music notation, things like that. Anything that sort of has a two-dimensional representation, it makes sense to be able to use a tablet or a stylus to enter that information, because you don't have to worry about some one-dimensional language that you have to transcribe into the actual notation. And what this then provides us with is what I feel is some very relatively new interaction methods and styles that focuses specifically on STEM education, right? STEM, science, engineering, science, technology, engineering, mathematics. So our sort of overall vision is that we want these pen and touch-enabled devices to offer natural user interfaces, natural user input, as I said, close to pencil and paper, pen and paper, and provide an easy learning curve to be able to use some of these tools. And in order to do that, what we need to do is do sketch recognition, and that sketch recognition involves the ability to do handwriting recognition, understanding mathematical expressions, understanding free-form drawings. And then what we end up doing is augmenting pen and paper with power of computation. Okay? And then what this does is then hopefully provide us with some interesting STEM education tools. So I've sort of structured the talk as a past, present, and future talk. So we're first going to go back a little bit. And when I first started this, I made the observation that these diagrams and illustrations that you see in physics books and mathematics books, they're useful for explaining mathematical concepts, but they only really aid you in the initial formulation of a particular problem. They're static. And therefore, what we wanted to be able to do was to try to make them more dynamic so that they would provide more information to the user as they are working through a particular problem or understanding a particular concept. And that's where mathematical sketching came from, which is basically the notion that you sketch diagrams, you write down mathematics, you associate the mathematics to the drawings, and then you perform some animation. And this was manifested in a prototype we call MathPad. And what I want to do is just give you a couple of quick examples. I know, this is old, but I want to give you a couple examples because we're going to see why we need to move forward with this and what the limitations are in the MathPad system. So let me go ahead and I'll start. I'm not going to worry about showing you that you can recognize handwriting mathematics. I mean, it's pretty much, math recognition is, I wouldn't necessarily say it's a solved problem, but it's pretty close to being a solved problem that, it just works. So I've written some I got some pre-canned mathematics here, and this actually represents damped harmonic oscillation. So I will go and I'll draw a ceiling and a little spring and a block. And I will nail these objects together, and then I will grab the mathematics and attach it to the spring. Needs a little bit of time here. There we go. And then I'll run it, and you see the animation. Okay? And that's all well and good. It gives you a sense of what's happening in terms of a dynamic illustration. And one of the other things that we did was I wanted to go further and see how far I could go with making the illustrations. So what I wanted to do was give the ability to actually write little programs, a little more sophisticated programs that would allow you to do various interesting things. So here's an example of air drag, right, or 2D projectile motion subject to air resistance. And what you see here is, there really is not a nice closed form solution for this. So what you have to do is you have to essentially doubly integrate the differential equation using a simple, you can use a cutter, or in this case I'm using Euler integration. And I go ahead and I draw my little floor here, and I'll say this is 100, and we'll put, we'll label this guy as P. Okay, let me turn sketch trails on, run it, and you can see that in this case, you can see how the air drag coefficient is sort of pushing the object so that it looks more realistic. And I'll just show you one more. This is sort of my favorite one. This is mathematics that represents the integration of a orbital motion differential equation. So I'll go ahead and I will draw something that looks like a sun. I'll label it, and then I'll draw a ball and label it P, and then I'll run it, and you'll see it does an orbit around. In this particular case, the orbit is a circular orbit, approximately circular. And the cool thing about this, when I designed it, was that you could just change a variable. So I'm changing the initial position of the object, and I run it again, and you'll see that it provides you a nice sort of dynamic behavior. So it really gives you the ability to sort of see how different parameter changes affect the animation. Okay? Now this was all well and good. But the problem was that we had to essentially provide a full mathematical description. And that's okay in some cases, but if I'm trying to think about how we want to use it more in a physics class, we needed to sort of deal with some very fundamental problems. And that's where we get to the present. Okay? And what we're interested now in doing is sort of taking mathematical sketching in MathPad and trying to bring it into intelligent tutoring. And the features of intelligent tutors, of course, is that it helps build students' knowledge, it helps them understand problems, and provides scaffolding to help them as they work through problems. And in this case, is another ideal situation for pen-based interaction because students are used to solving these problems on pencil and paper. and once again it provides a more natural interface. And then what we can do is then use these animations to provide intuitive concepts, or intuitive understanding of these concepts. Now, here are a couple of physics problems, a couple of simple ones I pulled off the internet. In this case, we've got a 200 Newton block is suspended by 3 cables, and we have to find the tension in each cable. Now, if we were to take this and try to animate it in MathPad, we couldn't do it, right? Because, first of all, the problem is not asking us to specify how an object is going to move through time, or how we might integrate a differential equation to have an object move through time. It's not asking us that question. It's asking us to simply find the forces that represent the tensions in each wire. Here's another one. In this case, what we've got is we've got 2 blocks, one on top of each other, and you're pulling them across the floor, and you've got kinetic friction and static friction happening with each of the blocks. And you want to see what the maximum force will be before the block on top actually starts to move in the opposite direction. Okay, once again, we couldn't do this. We can't do this in MathPad because, you know, it's asking us for a simple number, an answer, all right? And what we find actually in most physics books, especially in high school and, you know, introductory books in college, is that 90% of the physics problems ask for a number, or, you know. And therefore, we need to improve mathematical sketching capabilities in order to support this type of thing if our overall goal is to provide an intelligent tutoring system with mathematical sketching. So how do we go about doing this? Well, we have to, once again, as before, understand the sketch that the user has written. We have to understand the mathematics that the user has written. We have to try to facilitate the student learning in some way, and typically with the scaffolding or other types of tools. And we don't want it to be so burdensome that it's too difficult to use.
So I'm just trying to understand the difference between the previous class of problems that you felt your tool could handle previously and the next set of problems that you've identified. So the previous class of problems was about just doing animations.
Yeah, it was basically about doing animations and trying to illustrate things dynamically with the caveat that you needed to specify how things moved through time. In all the examples, you always would specify something as a function of time, whether it was a closed form solution, f of t equals t or whatever, or whether you actually had to take a differential equation and solve it. Okay? But each one of those, in each of those cases, the problem was always specifying how am I moving at each time step.
So I do recall from my physics classes that there used to be 2 different kinds of chapters. One was talking about statics and the other one was dynamics. So the previous thing was more about dynamics and now you're talking about statics.
Yes. Okay. That's a very good question. It turns out that in both statics and dynamics there are problems that we want to animate. We want to provide animations that provide insight into the problem in both cases. And you're going to see an example of how we do that for a statics problem. Okay? So, obviously the goal is to do a richer set of animations and develop an understanding of the problem and so on. And then as a result, we can hopefully understand the student solution. And what we've developed is something we call Physics Book, which is the next generation of MathPad. And what I want to do is show you some videos of what Physics Book can do in its first version. All right. And what I'm going to highlight, I'll highlight some of the features as we move along, and then we'll talk a little bit about some of the details. So let's go to the first video. Okay. Now, I apologize for it being a little bit slow, but when we recorded it using Camtasia, it took a little of time away from the runtime. So, now in this first example, one of the things that we did was we added a physics engine into the system. So we have an underlying physics engine that sits behind the scenes. All right, and what that allows us to do is it gives us lots of flexibility. We can simply make a drawing without having to add any mathematics at all, or we can go ahead and actually supply mathematics to and associate that to the drawing. So in this case, what we're doing is we are applying basically position, right, as a function of time, which is what MathPad had before, because we want to make sure that we've got the functionality that we had in MathPad into the new version, right, because I'm trying to keep it and then expand upon it. So in this case, what we're doing is we're writing the equations of position, and you can see this is sort of a projectile equation in this case. And we've added some things here. You'll notice one of the things that this is in real time, that the recognition is in real time. It's not, you don't have to circle it and then have the system recognize it. It's recognizing it in real time. And what you're going to find here is that there's an initial bump up and then it drops down. Some other differences as well you'll notice is that we actually do an analysis of the drawing and then we beautify the drawing. And this was something that we decided to do to make it a little bit more easier to understand. And you'll also notice there are vectors that are attached to any object that show you what's happening as you move through. All right, and we put a ground plane in there to see. Let's see this one here. So that one we showed with position. This one we're showing velocity. So we have the ability to enter velocity equations, position equations, acceleration equations into the physics engine, and the physics engine understands those equations and then essentially throws them into the overall physics engine architecture and allows us to do that. Okay. Let me see. Do I want to show this one? I'll show this last one here. This one's a little bit interesting as well because we use two springs and she make two springs and then we have a circle or a sphere that we put on top of this structure. And in this case, all we need to do is essentially just enter the mass of each of these objects. And so what this does is that it provides flexibility in terms of what you can specify into the system, right? If you want to do a full specification, you can. If you want to do a minimal specification, you can, and that's important.
So, Joe?
Yes.
So in this, are you assuming that the sketch recognition is always going to be perfect, or what happens, or how is the communication between the user and the sketch engine tool?
Well, first of all, if something is not recognized correctly, what we end up getting is the ability to simply erase that offending ink. We would call it the offending ink, and then rewrite it. Or if one of the drawings is not recognized correctly. See, the beauty about this is you can simply just erase it and do it again.
So my question was that how does the system know that it has not recognized the drawing correctly as opposed to giving it a different interpretation and going back to the user and saying this is the part?
Yes. Okay. Well, right now it doesn't necessarily know that. It's sort of, we're making the assumption that you're doing things correctly in terms of setting up the problem, right? You're going to see an example where well, let me show you. Okay. Yeah. Go ahead.
Can you turn off the beautifying of the pictures? They look much nicer.
That's an interesting question. Currently, we don't turn it off, but we certainly could do that. One of the interesting things about leaving them in their natural state is you have to make sure that the underlying representation exists so that you can do a proper animation, because unfortunately when you make the drawings they're not precise, right? They're imprecise, so you have to do some rectification. And what we did was in this case was actually just do the rectification and show that to the user. But that's something that we could add very simply as part of it. I know I like to always trying to maintain that notebook style, if you will. Did you want to say something?
Just about this point. So the goal here is really to allow the user to be able to animate it given any form, whether he gives no equations or he gives partial. So if he just gives you a value for velocity, you should be able to animate. This gives you the equation for velocity, whether in vector form or in XY coordinate form. So the focus really was to making that work, not files. But that could be that's a really important.
And I'll talk about some of the more challenging issues that we're struggling with right now as we get through. So here's another, this is actually was like, that was the video that I showed you was physics book version 0.5, okay? And now this is physics version 1. So you'll see a few changes here, a little bit a different style. And what I wanted to show in this case was, so here we're going ahead and we're doing, once again, creating the velocity vector, and then going ahead and writing down the vector equation. And you're going to notice something here is that A is not actually specified. Right. And in this particular case, since A is not specified, you're going to see that it's not behaving exactly the way we want it to. So we just go ahead and we can replace A with G, and G is a gravitational constant. It's built into the system. And we go ahead and we run it again, and we'll see the behavior that we want.
You have it show you sort of the relevant built-in equations and constants that it's using?
Yeah, you can do that. We don't do that. Well, actually, over here you can see it. It says what gravity is right there. Yeah. So now, as you can see, we're starting to get into a little bit more of the problem domain. We're actually a specific problem. So we're trying to find the force that acts on this object. And we go ahead and we, over the pre-written math, or we've already recognized it, and drag it to the object. And actually, in the very latest version, you don't have to do much actual circling and dragging to the object. It kind of does it for you. So once again, we have the ability to experiment with different values. So you can see we're trying to keep stuff that was in MathPad and bring it into the new system. But there are subtle differences here. Let me see here. And of course, when you hover over the object, it shows you all the mathematics that was associated with it to help you understand what's going on there. And then as one of the ways to keep track of current values is we actually show those to you right when we're on the drawing. So here's an example where, a little bit more sophisticated example, where we're looking at modifying an inclined angle. And you can see that we use a slight adjustment there into what the actual angle was, and we associate the mass to the ball, and then specify the normal force. And what you can do is look for different quantities as you're animating, so it shows you the actual the sum of the forces as it moves through the animation.
Is it sliding or rolling?
It's sliding, rolling. It's not rolling, it's sliding. Now here's sort of the one that with the initial problem we looked at. We've got the tension in two wires attached to a block, and we go ahead and we make the appropriate associations. As you can see, when we make those associations, the drawing gets rectified. And they want to find the tension. So then what happens is, once we associate the tensions to the individual wires, we're going to run the animation. And this is something that's very interesting because there is no animation. And there shouldn't be, because we're in equilibrium. So what we're doing actually here is showing that you've gotten the problem correct by not showing any animation at all, because that's what the problem calls for. Now, if the user made a mistake in calculating that tension, let's say, they chose a different value for it and it calculated a different value. What we would get then is you would see, you'll see what happens. So the tension wires break and the object falls. So what we're trying to do here then is visually demonstrate what is happening with a problem, regardless of, and so it's not specifying equation of motion. In this case, what we're doing is we're taking it in the opposite direction. We're saying statics problem. If you get the problem right, nothing should move. If the problem is wrong, it won't move. Yes?
How did the system know that it was incorrect? I mean, that it was incorrect because the problem could have been that the tensions were, in some weird state and then.
Well, yeah. I mean, we sort of make underlying assumptions.
It's a statics problem.
Well, I mean, we know what the tensions are, and if you look at the sum of the forces, right, you'll be able to determine whether or not you're in equilibrium. And if you're in equilibrium, the forces are equal to 0, therefore nothing happens in the physics engine, right? So that's kind of the way it works.
So but you're making the assumption that the way the problem is drawn is that it is an equilibrium state problem and not like a specification of state in some moment that could have occurred such that you'd end up with this other kind of behavior.
Yeah, pretty much. Yeah. I mean, one of the interesting things about this stuff is that we sort of have all these physics problems to go by as effectively our sort of skeleton problem domain, and we can take some liberties in not having to deal with all the absurdities of physics and stuff. No. Okay, so anyway, that's an example. Let me go back to the slides.
So Joe, I have one question on the user interface here.
Yes.
So instead of writing down things on the side and then associating the math with the object, can I just annotate the object with an arrow or something that we would normally see happening in?
You can, yeah. A future version will. I'll briefly mention some of that later. All right, so a little bit about stuff under the hood, what's happening, okay? And the basic architecture is relatively straightforward. We've got the user interface, which deals with the ink and the gestures, and then renders the animations. Then we've got a sketch analysis component, which deals with the recognition and the rectification component. And then the simulator, which represents the physics engine, which not only has the physics engine, but also deals with specific entities such as springs and wires. And all that sort of flows with the association inferencing system, which allows us to associate the math to the individual drawing elements. Now, probably the most interesting part of this is the physics engine, because we could not simply use an off-the-shelf physics engine, because what we needed is one that provided us with a way that we could sort of inject mathematics into it as it's running. So what we did was we based it on a typical game physics engine, and it uses traditional approaches in a certain sense. So the position is updated by a double integration of the acceleration or a single integration of velocity. And then the collision detection and resolution is sort of standard, although what we do is we use exponential smoothing to keep track of net motions, which is very important when we want to do rest and sliding contacts, okay, because that turns out to be really tricky. But then what we can also do with it is we can replace the update equations with any equation we want. Right? And then what the system does is it looks and it figures out, okay, this is a velocity equation, this is acceleration equation, or this is the position equation, and then throws that into the physics engine, and that takes over. Okay? Now, then you might ask, well, what happens if you collide with something, an object? Well, unfortunately, in those particular equations, the user is not specifying what happens after a collision takes place. So what we simply do is we just break the user-defined behavior once a collision hits, which makes sense, right? Because that's sort of the best you can do with the user-defined behavior, unless you actually provide information about what happens when you collide with another object. And then, of course, we provide what I call hooks into the physics engine, and those hooks are for other things. Other physics concepts, and we'll get to that when we talk about sort of the version 2 of physics book. Yes.
When you say collisions break user-defined behavior, you mean that you just stop the system as it is, or you compute a new set of forces using more sophisticated some physics?
What we do is, once we know we're going to get a collision, we sort of say, all right, the user-defined equations are no longer, let's take sort of the last piece of information that we can from those equations, and then use that to feed that back into the physics engine to calculate new forces and positions so that we get it. So it's a sort of a continued flow, right, in the animation. So in terms of recognition, we do some relatively straightforward things in the recognition. All ink strokes are resampled. Then we do that to remove noise and ensure that all the points are equally spaced. And we also made an observation that typically the diagram components that you draw are going to be larger than the mathematical expressions, and that helps us to distinguish between a drawing and a particular mathematical symbol, especially if we're labeling a particular drawing. And then in terms of the recognition, we have to recognize first recognize the diagram components. We look for specific shapes, wires, and springs, and then the remaining ink strokes are recognized as mathematics. In terms of shape recognition, we do some very straightforward things. We look at number of cusps and self-intersections. Cusps are just components that have very, very high curvature. And if the stroke is closed or not, that also gives us a sense of whether or not we're dealing with polygons or circular objects. And we use a measure of circularity where we look at the standard deviation of the angle about the centroid, and that also gives us a good indication that we're dealing with a circle. So, we're very, very simple with the shapes that we have right now. Polygons and circles. Circles, you've got 2 cusps and a high accuracy, or a high circularity, and then with the polygons, you've got more than 2 cusps. And of course, as we move forward, if we want to add other shapes, we'll have to get more sophisticated. Now, in terms of wires and springs, we sort of handle them a little bit separately because they sort of have unique structure to them. One of the things we have to do is we have to make sure that one end touches a recognized shape. And so with springs, you have to have more than 3 self-intersections, and with wires, they can be relatively straight lines. Okay, so that's a way to sort of make the determination between those. And as far as the mathematics recognition, as I said, when I started doing all this stuff, 5, 6, 7 years ago, something like that, math recognition was people were still working on it and stuff, and I did my own math recognizer. But now we sort of, have some pretty good math recognizers out there, and we use one called StarPad, or the mathematics recognizer in StarPad, which was actually funded by Microsoft when Microsoft was supporting the Penn Center at Brown University. So it's a pretty nice system and works pretty well. Now, the other thing that we have to be able to do in trying to go from a sketch to an animation is what we call rectification. Rectification sort of says, let's take the drawing and get it ready for an animation by dealing with, by going from approximate to precise. Okay, because if you want to make it look proper, you have to make sure you've got precise specifications in your drawings, even though they may look approximate. And this can occur during the recognition process. It can also occur when you make associations between objects. And we saw an example of that where we changed the angle of the inclined plane, and then in doing that, we actually changed the triangle. And this can be applied to both individual items or groups of items. So in terms of shape recognition, one of the things that we sort of ensure is anticlockwise ordering of the polygon vertices. We do that because it makes it easier to understand how we want to do the rectification. We also deal with vertical and horizontal alignment of edges. So if you draw something that's approximately horizontal or approximately vertical, we're going to treat that as vertical or horizontal. Other cases, for example, let's say that I draw, classic example is with the inclined plane problem, and I draw a circle on top of it that represents a ball, right? Well, what does that mean? Should that ball be on the circle? Should it be within the circle? Should it be above the circle? We sort of make the assumption that what you're trying to do is have the ball placed on the circle, and we move it there to make sure that that's the proper. Associating the angle with a particular vertex of a triangle is a little bit tricky because Depending on how the triangle is drawn, we have to figure out exactly what angle that we're moving. So we have a different algorithm for different cases in the way that triangles are drawn differently, in terms of different orientations. Now, in terms of the springs and wires themselves, one of the things we have to ensure is that you may draw a spring or a wire and it may go inside the box a little bit or right above the box. Well, we make sure we identify the object, and then we make sure that the end of the spring or wire is actually touching the block, let's say. We also support vertical and horizontal alignment in this situation as well. Most of the time, what you're dealing with is a vertical or horizontal. But as with the tension example, sometimes it is at an arbitrary angle. Okay. All right. So that's just really a little bit about what's under the hood. I didn't want to get into too much detail with that because that's really not the purpose of the talk. Now, what I want to talk now about is the future, where we're going, and this is where the really interesting stuff is starting to happen. And what I want to talk about right now is a relatively important strategy that we've come up with, and it's actually really, really simple, but it makes a lot of sense if you think about it. And we want to be able to support, our ideal goal is to support 100% of all the physics problems in a Physics 1 textbook. That's our ultimate vision, right? It's also a very challenging vision. So in order to do that, we need to be able to have a lot of coverage. So we started thinking about strategies and ways that we can get as maximum amount of coverage as possible. And one of the ways to do that is if you look at Newtonian mechanics, you see that force equals mass times acceleration. It represents the fundamental equation that all the other concepts are relatively based on. So if we have an understanding of how the other concepts in physics that are not directly related to F equals ma, how they translate to F equals ma, then if we can identify what type of problem we're doing, then we can figure out what the mathematics is necessary to go from whatever concept we're interested in to F equals ma. And if we can do that, then we can do an animation of something. Therefore, what I'm saying is, if I do a problem with work, where I'm asked to find the work of some object, or the kinetic energy, or the momentum of some object, or potential energy, for example, I can then translate that information into F equals ma and then do an appropriate animation. Okay, so that really expands the type of problems that we can support, and that's one of the strategies that we're working on now. And that's where Physics Book version 2 comes into play, and this is sort of present future because it's under review right now, so I can't really talk too much about it, but I'm going to just give you some of the highlights. And you'll notice we're starting to make it look more and more like an intelligent tutoring system. You can see we've actually got the question up there, and in this case you've got a mass that is lifted by a certain height, and the force is applied by a person pulling on the rope, and you have to find the work done by what happens when you raise it by 4 meters. So what you actually do is calculate the work, and then the system, right, will tell you whether or not this object moves 4 meters. And if it does, based on this work calculation, you got the problem correct. And if it doesn't move 4 meters, then you know you didn't get it correct. Okay. So that's sort of the next generation. And in order to do that, we have to sort of add some other types of things to the drawings. Right. In this case, we're adding a displacement to the drawing. And this, frankly, is something that you would do anyway as a student. Right. The proper thing to do. Right. Maybe not all students would do this, but it's the proper thing to do going through the process of solving these problems. So not only does it help you make the animation work, but it's something that you should do anyway. And so what this allows us to do then is Newtonian mechanics, kinetic energy, potential energy. We can do simple pulleys, inclined planes, things like that, where you're actually not specifying, where for example, you're specifying just a force or a work or whatever. And that really sort of helps to make it much more robust to starting to think about using it in a physics classroom. Obviously, our ultimate goal is to get it in front of physics students and have them use it for a semester and then see what happens. All right. Now, all of this sort of leads into what we're sort of thinking about now and into the future. And one of the things that I realized was, what you could do is have a set of canned problems and understand those problems completely and then provide them into the physics book. But I don't think that would be that very much fun. So what I'm interested in doing is taking any problem and trying to understand what it's telling me. And if I know what the problem is, if I understand the problem, that will lead to an understanding of what solution you might do in order to solve that problem. So what we've been doing is actually, we have a rudimentary version of this. We do natural language processing on the physics problem itself to extract important pieces of information. So we look for things like, number quantities, what the problem is asking for. We look for keywords, velocity, pulley, acceleration, force, things like that. And from that information, we can then, or as our goal is then to define exactly what the problem is asking. And if we understand what the problem is asking, then we know the types of solutions that we can have for that problem. And if we know that information, then we can provide the scaffolding necessary. So as they work through the problem, we can identify where they are potentially in a reasonable set of steps that you would go to solve the problem and provide help along the way. So that's something that we're moving forward with. And then what we would have essentially is a knowledge base of solutions, right, based on certain concepts. So we know if we have a certain concept, we know that this is the approach, general approach you would take, and then you would try to match that approach to the actual problem. Now the other thing that we're realizing that we need to do is bring the solution into the drawing. Okay? One of the things we're also realizing is that some problems don't provide us with a good way to animate them, to show that you've got them right. The way that I describe this to laymen is I say, think about the back of the book of your physics book, right? And these are the answers. What I say is, what physics book is the greatest question and answering back of the book you've ever seen. That's our ultimate goal. And some problems just don't amend themselves to this type of behavior. So we've been thinking about ways in which we can fix that. As an example, okay, let's say I have a problem that is asking me at t = 5 seconds, what's the height of a projectile? Okay, so you write down the height. Now how do we animate that? Because you could have the object animate, in the projectile motion, but at 5 seconds, how do you know that you've actually got it right? So we've been thinking about providing a mechanism where we can throw the solution, we can have the user actually enter the solution into the problem. And for example, something like this, you've got a ball here, and this is the height, or that you want to get to, and let's say it's at t = 5. And I can say, all right, just doing this, and I say that the height is going to be 10 meters, let's say, right? Then what we could do is then animate this piece here to show that as this ball is moving, right, then this is going to increase and decrease with the height of the ball, and then at t = 5, we show what is that value? It's equal to 10. Okay, I know I got the problem right because, that's the answer, right? And we would have something like this that would say this is 0 and this is, 10 units or whatever. So we're thinking about ways in which we can add this type of behavior into the drawings so that we can then provide an appropriate animation that makes sense. Now, not every problem is going to be animatable, as I call it. They just don't facilitate that. But what we're trying to do is figure out ways in which we can do that as best we can, right? As many problems as we possibly can. Okay, so basically what I've talked about today is mathematical sketching I believe is ideal for intelligent tutoring systems, especially in the physics domain. And I think physics are a classic example because of the fact that there's so much motion involved. I mean, physics is really about motion. And what we've done is we've sort of developed a new system called Physics Book, which is starting to look at how mathematical sketching can be brought into an intelligent tutoring system. And we've developed a couple of different versions, and we're continuing to work on it. The big thing is integrating the physics engine into the system because it provides more flexibility. in how you specify a mathematical sketch. And we're also, that also amends itself to being able to do problems we couldn't do before, such as these static problems, or problems where it's asking you for other quantities other than force or acceleration. And of course, understanding the word problem itself is, I believe, very important, and will go a long way to helping us understand the student solution on a high level. I refer to it as high-level semantic recognition. Right? Mathematical expression recognition is you recognize the syntax, then you recognize the parse. High-level semantic recognition is understanding that that equation that you've written is an equation of projectile motion or an equation for kinetic energy. If you can understand that type of thing, then it also goes a long way to helping you understand what's going on. And of course, there's tons of more work to be done, which is why Salman is going to be working on this problem for many, many years to come. And we'll do a great thesis. So I just want to thank my sponsors. The primary work is supported by the Career Award, and I'll take any questions that you have. Any questions?
The automatic, sort of the natural language processing you do on, so the idea there is to just sort of copy and paste some existing word problem?
Yep, you would copy it, you get it off the internet, or you can actually write it too, if you wanted to.
So it seems like that might be error prone.
Could be.
Is it in practice?
Well, I mean, we're really just touching the surface on that right now, and what we have is the ability. It actually extracts extracts variables and important keywords and numbers, and then what it does is it says, okay, given this variable, tell me all the mathematics that I think would be related to it in terms of physics problems. And that's really where we are at this point. And then what we have to do is incorporate it into the physics book system, and then that will hopefully provide us with more information. But it's one thing I didn't talk about was what happens when things go wrong.
Yeah.
Right? That is a huge problem. And I've sort of been punting it for a long time because it is such a hard problem. And I wanted to focus on trying to actually do the first problem of seeing what type of animations we could make. Right? But at some point we will have to tackle that. And that's where, reinforcement of problem, math, and drawing all together can hopefully help provide enough information to let us know what's happening, what's going wrong, so that the user can actually enter things if a mistake is made.
Yeah, it seems like for this part in particular, though, with understanding word problems, that could be something, that it's experts or other people could sort of annotate them. You could maybe have a library.
You could do that, right? And that's one way to go. I mean, there's work. Guy by the name of Kurt Van Leen, who's now at Arizona State, I believe. He formerly at Pittsburgh. He developed something called the Andes physics tutoring system. And what Andes does is very similar to what physics books does, except it's not pen-based, doesn't allow you to write anything. And what they've got is a set of canned physics problems. And because they've got those canned physics problems, they know the exact steps that you need in order to solve that problem. And they provide the scaffolding. And I thought, yeah, I could do that, but I don't know. I wanted to be cooler, I guess, and try to do it automatically.
Well, it seems like there could be a lot of sharing of, how to do.
Yeah. I mean, but that also begs the question too. Is I can solve a kinetic energy problem in a number of different, I can solve a force problem in a number of different ways, right? Or like if I'm asking for the velocity, I could use kinetic energy to find the velocity, or I could use force to find the velocity, right? So that there's multiple ways to solve the problem, and then how do you deal with that? Can you identify that there are multiple ways to solve the problem, and then figure out that the user is actually taking one of those paths, which is also very interesting.
Tell somebody that's wrong.
Yeah. Yeah, so that's a lot of it, I guess that's why they call it a career award, because I've been doing this for the rest of my life. So, any other questions? Yes?
So how far do you think are we from using these systems in real classrooms?
Well, it depends on the system. The simpler the system, the more readily available it will be. in the classroom quicker. As an example, we have a system right now which animates simple data structures for CS1, linked lists, trees, things like that, where you actually sketch out a linked list, you sketch out a tree, and then you actually write code, and then the code will animate the drawing that you made. That we're going to use it starting in the fall. It's relatively straightforward. For something like this, there's so many different pieces and so many different components that it's going to take a little while. But I think what will end up happening is we'll end up doing it on a very constrained basis, where we'll say, here, we want you to use this for this particular physics concept, and you're going to spend 2 weeks with it. We're going to make it really robust for that concept, and then see if it actually helps people. But actually saying that I can take this and give it to a physics 1 professor and say, all right, all your students should use this throughout the whole course is a long way off.
So are you targeting here high school, advanced high school curriculum, or do you think it's more of undergraduate curriculum?
It would work for both AP Physics in high school and also Physics 1 for engineering and non-engineering majors.
One difference between the CS1 system that you talked about and this one is that CS1 is presumably for undergraduates.
Yes.
And there probably it's easy to force the students to use the system. But bringing this technology into high schools might have another totally different set of non-technical problems.
Yes and no. The high school teachers that I have talked to would be very, they would love to be able to use it. But of course, we would have to provide the hardware that would enable them to use it, right? Typically what we would do is have a portable tablet lab, and then we'd have them, obviously having them take it home would be, you could do that because this would work with a simple Wacom tablet device. Thank you to Windows 7, right? It enables you to do pen anywhere, as long as you have the right hardware. So yeah, it's really just based on the scope of the experiment that you want to run when you're using it with the students or the teachers. And one of the things that we can do right now, very close to being able to do, is actually have the teachers use it to teach with. Because they're it's a more constrained, user-defined set. And then what the other thing you can do is you can look to see if the students themselves actually gather more understanding when they're being taught with this tool than if they're not being taught with the tool. And that's something that we definitely should be able to do. But yet, as I say, giving it to the students, and say, whole semester you're going to use this, that's going to take a while.
One other silly question. So do you also envisage these systems being used on smartphones, smaller smartphones, as opposed to with the tablets?
That's also a very interesting question because, we're in the world of touch now, right? I mean, I was at Kai 2 weeks ago, and maybe there were like 30 papers on touch, maybe 40. How many papers are on pen? 0, right? A lot of stuff on phones and things like that. I think you could potentially do something on a small device. The problem with a small device is the handwriting and entering the mathematics. And that poses a bit of a challenge because, first of all, you have a much smaller screen space to do it. You typically don't have a stylus, although some phones do. I know that there's been some work in trying to recognize simple characters using your finger. There's actually I believe there's an Android application out that allows you that does character recognition with just writing with your fingers. But simple characters is a lot different from x squared times the square root of x plus 3 over 2, right? So it's possible. The other thing that you could do, and it's something that I've thought about too, is you don't provide all the functionality to somebody on the phone. Maybe you just provide the animation, the viewing capability, so they at least get to see things, and then provide them with the ability to change parameters, right? So from sort of a student learning point of view, you're not giving them everything, but what you're doing is you're giving them at least enough machinery to explore, Right? And it may not help you in solving the problem, but at least it will help you explore the the visual, the physics concepts. So that remains to be seen, I think.
Any other questions?
Do you actually depend on pressure information from stroke, or do you just use discrete stroke?
It's just discrete.
Binary stroke. Because
Yeah.
then you could use a capacitive stylus.
Yeah, the thing about pressure, I actually, when I first started doing this, I was using pressure, and I took it off because.
No, I wasn't implying that you should use pressure. I was just
Oh.
I was saying since you don't use pressure,
Mhm.
you could use capacitive styli on touch devices.
Yes.
Yeah.
Yeah.
The pen digitizer rate is generally not as good on
Right,
on
but
tablets.
yeah, one of the things you have to be careful with those types of devices is your hand can get in the way. So you end up writing like
Yes, it's true.
but there are some pretty decent palm rejection algorithms out there that work. So yeah, definitely. Mm-hmm. Anything else?
Okay, so let's thank the speaker again.
Thank you.